The next speaker is the Naama Pearl, which will talk about noise-aware NeRF. And this is a joint work with Tali Treibitz and Korman from Haifa University.
So, hello everyone, my name is Naama, and I will present today our work NaN, Noise-Aware NeRFs for Burst Denoising. This work was part of my master's degree at the Marine Imaging Lab under the supervision of Tali Treibitz and Korman from the Computer Science Department. When we capture images in limited light conditions, such as dark, bad weather, or underwater, we can barely see anything. We can change the brightness of the image, but this reveals large amount of noise that prevents us from observing fine details. In our method, to denoise this kind of images, we take the approach of burst denoising. In general, burst imaging is a sequence of images captured without necessarily using a tripod, resulting in images from different viewpoints. This approach is commonly used also in smartphones to solve various reconstruction tasks. When these images are noisy, they can be jointly used to produce a cleaner version of some target view. And the main challenge here is in overcoming the misalignment between the views. To solve this problem, in one line of research, a CNN is trained to predict per pixel per view kernels, which simultaneously align and average the burst. For computational reasons, the kernels are limited in their size, so they can only handle rather small misalignments. Another approach, based on NeRF estimation, uses optical flow to compensate for the motion. This approach is really nice result, but they struggle when it comes to large misalignments and under high noise. And you can see photography apps ask the user to hold still while shooting in night mode. In this work, we take an approach that considers the 3D structure of the scene, which is significantly more robust under such conditions. Our main insight is that the burst denoising problem can be formulated as an image synthesis problem. The difference is that instead of denoising an existing target view, the goal in image synthesis is to generate an new image as it would appear from the target view, and usually under the assumption of perfect imaging conditions. We leverage the ability of novel view methods to implicitly learn the 3D structure of the scene in order to align and merge the images in the burst. In particular, the NeRF line of research has shown impressive capabilities in rendering and scene understanding. We build on one of its follow-up papers, IBRNet, which can generate novel views given small number of input images and without per-scene optimization. In this way, we don't need to train a new network for each image we want to denoise. I will next overview the IBRNet framework and describe our addition to make it noise-aware. So IBRNet projects an array out of each pixel and looks on the object that lies on it. It predicts two values at each discretized 3D point along the array. The first is density, denoted by ρ, which describes the existence or non-existence of object at each 3D point. The second is the RGB color of the point, denoted by C. The final color of the pixel is an integration of the color at each 3D point, weighted by some function of the density along the array. The weight of a 3D point will be high when its density is high, and when the densities up to this point are low, meaning that this point has an object that is not occluded by closer objects. To understand how the network predicts the color and densities at each 3D point, let's examine the exact 3D point that intersect with the 3D object. When we project this point to each of the other views, the incident colors are all in the same colors, in this case green. But if we project a different 3D point that lies in a free space to each of the other views, the incident colors are likely to be different. This is a non-Q in multi-view reconstructions. The consensus along views implies a 3D point with high density and a particular color, and large deviation between the views implies a low density 3D point, and the predicted color does not affect the final rendering. According to this principle, IBRNet predicts the densities and color at each 3D point along the ray. In more details, for each 3D point, IBRNet collects the incident pixel colors together with corresponding feature vectors that are extracted from a pre-computed feature maps for each of the views. This yields an extended features that are the input to the network. So the network applied on each 3D point as follows. First, some inter-view statistics are calculated, and then they are fed to one block that predicts the density, rho, and another block that predicts n weights that are used in a weighted average of the incident pixel colors to obtain the color of this 3D point. So this is the IBRNet framework, and we performed a detailed study to analyze its performance in the presence of noise. Here we show the behavior at 3 pixels from the test set. In clean images, the predicted densities along the ray are sharp delta functions at the correct depth. The corresponding RGB values that contribute to the final integration are scattered here in RGB space and look like almost like a single point in space. When introducing a significant noise and retraining the network with the noisy images, the predicted densities spread out. Interestingly, in order to reduce the high level of noise, rather than incorporate only a single point in the final integration, the network has learned to incorporate larger range of 3D points, which in practice averages more incident pixels in the final prediction. As can be shown here, the contributing colors are highly scattered in color space. While this helps in reducing the noise, it is not optimal as it also involves non-relevant pixels. So this proved our initial intuition, but can we do better? So to allow the network to apply spatial denoising more explicitly, we modified the weighted mean to use a small neighborhood around each incident pixel and modified the weight to be kernels in corresponding dimensions. Another modification we made is in the way the information from the different views is aggregated. In practice, the density and color block operate separately on each of the views, and this makes the statistical calculation to be the only connection between the views that the network sees. In clean images, this was enough for the network to learn from. But the noisy case requires modeling of more complex connection between the views, and we propose to provide it by introducing an attention block between the input vectors. These contributions, and some others that I did not detail here due to the time limit, allows the network to predict sharper and more accurate densities. In smoother areas, like the bottom example, the network still preserves the density prediction as a tool for applying more spatial denoising. In the color space, the RGB colors are better clustered, which yield a better prediction of the images. For testing our algorithms, we use burst datasets from previous papers. This is an example of a clean target view. We then added to the images Gaussian noise. IBRNet produces a reasonable result, demonstrating the potential of the NeRF framework in burst imaging restoration tasks. In comparison, our algorithm manages to remove the majority of the noise while preserving more details and avoids the smeary artifacts. We also compared our method to 2 burst denoising algorithms. DeepRep produces a smoother image in the expense of eliminating some of the details and some visible artifacts. And BPN produces severe color artifacts due to the small kernels they used. We evaluate the methods on all bursts in the test set, and our algorithm achieves better results across different noise levels. For real-world scenarios, we capture several scenes in low light using a Pixel 4 phone. This is an example of a target view from the burst. After changing the brightness level, we get this noisy image, and the average of the burst illustrates the amount of displacement between the views. This is the IBRNet result, and this is our denoised version in which it's possible to spot more fine details like the leaves and the staircase railing. Since NeRF is trained to produce images that appear natural, its output may be more pleasing to the eyes, but it does not necessarily coincide with the original scene, as can be seen in the railing artifact and the elimination of the leaves. And BPN did not cope well with the misalignment, as you can see in the ghost artifact of the wall. And here is a teaser for a subsequent work of our lab. We developed a NeRF framework that can render underwater images by incorporating the medium into the rendering equation. By doing so, we also able to remove the water from the scene. And more details about it, hopefully next year. In summary, we showed the relationship between burst denoising and novel view synthesis. We analyzed the IBRNet framework in the presence of noise and suggested several modifications in order to use it for burst denoising. For more details, results, and codes, you are welcome to visit our project website. Thank you very much for listening.
Thank you very much. So we have a question here.
Great talk, thank you. You need to estimate 3D structure as a first step, I assume, using Korman to get camera pose?
So for the low light scene, sometimes Korman was not enough. So we used other softwares, Metashape. But yes, it's a requirement for the method.
So it can deal with low light and small motion situations in order to recover accurate enough camera pose?
So of course, this is a limitation with a method, but I've seen that also when the rotation wasn't accurate enough, somehow the learning process, since we don't have like, I don't know, 100 images around the scene, we only use like 8 images. So if the rotation is not the perfect rotations, the network can overcome it. And I can see it with rotations and also with, for example, undistorted parameters. So the network were able to squeeze the images a bit.
The network learns the camera parameters?
No, we pre-computed it.
Okay, thank you.
Thank you. So, I have a question, but maybe the next speaker can connect in the meantime. So, continuing Shai's question, so doesn't it make sense to reiterate after the noise to recalculate the poses to get better calibration and then improve results in this way?
I guess it will help. The original IBRNet also fine-tune the network like the NeRF doing on several scenes. So we didn't do it, but I guess it will improve the results.
Okay, thank you very much.
Thank you.
So.